So this video is starting off where the first truth tables video is ending. We had started with a truth table and we are converting that into our boolean expressions. This is the sum of min terms. Now this is one way of showing the sum of min terms. There's a simpler way of showing it, which is the shorthand version, where you would say f as a function of a, b, and c equals the sum. I'm just going to say sum so I don't have to confuse you with the formula entry in this program of the sum of all of these min term products here. So what we need to do is represent these as numbers again. So simple way to do that, we could just refill out this truth table as binary numbers. So we start with 0, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, starts on the other end there, 0, 1, 1, 1, 0, 0, 1, 0, 1. And again, what I'm doing here is every time I see a true value, or every time I see the variable name by itself, that is becoming a 1, such as this a and this b. But whenever I see a value inverted, so that's c naught, I'm replacing that with a 0. And then this is 1, 1, 1. So now to show this min term in the simplified shorthand method of showing this, what we would do is for each of these columns we can just, in fact I'm going to add a column here, insert column before a, and I'm just going to number in decimal each one of these rows by this converting this binary number into decimal. So the first row is 0, next one is 1 because we have 0, 0, 1, the next row is 2, next row is 3, 4, 5, 6, and 7. So this is our decimal. Decimal representation of the row number. And so now what we need to do is look for whenever this is true. Every time this is true, we have a min term product here. So this is true for row 1, so I'll put 1, comma. It's true for row 2, so there's 2, comma. It's true for row 3, so that's 3, comma. We're skipping row 4 because that's a 0. And so the next true statement on the output is row 5. 5, comma. Then we have 6, comma, 7. Because 7 is true as well. So that's the shorthand method of showing the sum of min terms. Now, say we're given this method and we want to fill out a truth table. So I can delete these. What you would do is you can number these columns in decimal if you would like, but every time you see a row number here, you would put a 1 in that row number. So we have row 1, which we always start counting at 0. So row 1 is actually the second row. So we have a 1 in row 1. Row 2 is also in that list, so we'll put a 1 there. Row 3 is in that list, we put a 1 there. Row 4 is not, so we're going to ignore it for now. Row 5 is in the list, so we'll put a 1. Row 6, so we'll put a 1. And row 7 is a 1. And now we can actually go back and fill in all the blank spots with zeros. And you can see this is the exact same truth table that we started with. Now if we were given a Boolean expression and we were told to turn that into a truth table, we can do that as well. So let me make up a Boolean expression. I'll say A naught and B naught and C naught. And this is not simplified. You don't want necessarily to have a simplified Boolean expression to fill in the truth table, because you need to expand it for all the instances. So for instance, if I'm given an A and a B in a simplified Boolean expression, what I would have to do is actually expand that, because this is actually AB is actually A and B and C, or A and B and C naught. And using the distributive property, let me write that out. So AB equals A and B and C naught, or A and B and C. And using the distributive property, we have C naught or C and AB. And we know that C naught or C is actually a 1. So that's how we get the value A and B and 1. And that's another thing that we should notice, is anything ended with a 1 is the anything that you start with. So whenever we're given something like A and B, we want to expand it fully so that we can have one term per row for our true statements for our truth table. And let's say that that's all we have as true in our truth table, these 3 statements. And so we have A naught, B naught, C. What we would do is just convert that back into the numeric form. So when you see A naught, that becomes a 0. When you see B naught, that becomes a 0. When you see C naught, that becomes a 0. The next one would be A and B and C naught. When you see an A by itself, that's a 1. A B by itself is a 1. And C naught, again, is a 0. And then we have A and B and C. So none of those are inverted. So we're just going to say 1, 1, 1. So each one of these now, you would find it in the table, 0, 0, 0, and put a 1 in the output statement here. The next one that has a 1 is 1, 1, 0. So we'll put a 1 here. And the last one is 1, 1, 1. So now all the other ones that are in the table that are not mentioned specifically in the formula would get a 0. So this is the truth table for this statement. And again, let's look at if we were just given A naught, B naught, C naught, or A and B. And let's see if that's actually the same thing. Well, let me undelete this and then insert a new row, or a new column here after our original one. So let's find all the instances in which we need to insert a 1 in this new output. I'm going to call it G. And we want G and F should be equal, because all I'm doing is just applying these theorems to the A and B formula to expand them for the F column. Now I'm going to show you how to do it if you didn't expand it out. So we have A naught, B naught, and C naught, so that gets a 1. And then any time where you have both A and B as true or a 1, that's when you would put in a 1 in the output. So we have A and B as a 1 in this column, or in this row, and we also have A and B equal 1 in this row. And so you fill the rest in with 0, and you can see that column F matches column G. And hopefully that kind of clears up some of the issues you guys have been having.